Okay, so thank you for the invitation. So today I will be talking on the finite field isomorphism problem. We have seen a lot of isomorphism problems throughout the session. Let's see something interesting. Okay, uh, how does it work? Okay, okay, okay. Like before going anywhere, uh, okay. So I would like to start with assumptions. Like for cryptography, we need some kind of assumptions. And recently, there has been a lot of things going on regarding post quantum and stuff like that. And one assumption which came very promising is a lattice based assumptions. And what do I mean by lattice based assumptions? Well, by lattice based assumption, I mean the best way to solve some assumption is by lattice methods. And in this talk, I will give some counter example where I will show that even there is a lattice way to solve the assumption, that is not optimal and you can have some other ways to solve it. So this is the basic of this talk, and let's start with lattice. So this is already been discussed before, but just to start with, by lattice, I mean a discrete additive subgroup of Zn. And algorithmically, you can define a lattice using a basis over Zn. So the dimension of the lattice is basically the rank of the basis, and the volume is absolute value of the determinant of the basis. So when n is more than 2, there are infinitely many bases that generates the same lattice, and they are kind of connected by a unimodular transformation. So here I have a picture to give like some evidence. Like we have the same lattice, but that is generated by two different bases. Okay. So the problem that we are really interested in lattices is the shortest vector problem, which states the following. I give you some basis and you have to find the shortest vector in it. So the first question is, what is the norm of this shortest vector? So it really depends on what kind of lattice you are using, but we have this Minkowski's theorem, which states that the norm of this shortest vector is upper bounded by square root dimension times the volume to the power 1 over dimension. In practice, how do we solve the shortest vector? Well, we rely on lattice reduction algorithms. For example, we have this famous triple L, which is kind of a polynomial time, but only yields exponential approximation factor to solve it, of the solution. Then we have some more advanced lattice reduction algorithms. For example, we have Bicasi reduction that comes with an factor which comes with some parameter called block size, that is beta here, which kind of give me a better approximation factor, but now the running time is exponential on the block size. Okay, so this is what I wanted to start with a lattice background. So algorithmically, it's a hard problem to find the shortest vector, both in theory and in practice. Now, I want to give some reminders from the finite field. So for any integer, any prime integer q, I define fq to be the finite field with q elements, right? For any positive integer n, I define fqn to be the n degree extension of the finite field. So if we know a bit of finite field theory, it states that finite field are unique, but you can have different representations of it. So how do you do the different representation of a finite field? Well, you take any irreducible polynomial of degree n, like a monic irreducible polynomial of degree n, and you consider You consider all the polynomials over fq with this mod the irreducible polynomial. So you take different irreducible polynomials and you have different representations of the finite field. Now since they are isomorphic, how do you find the isomorphism? To do that, what you can do is you find the root of one irreducible polynomial in the extension, but in the different representation. And if you can find it, and this is already known, it's a polynomial time algorithm to find this isomorphism. And so if you know it, you know the isomorphism between two representations. So I just need this little bit of background on finite field theory to come onto the finite field isomorphism problem. So to define the finite field isomorphism problem, I need two representation of the finite field. The first one, which I called a private representation, is defined by a uniform sparse ternary irreducible polynomial of degree n. And let's call it little f, whose one of the root is x. Okay? And you have a public representation, which is like a uniform irreducible polynomial of degree n. Let phi be an isomorphism between the first to the second representation. Okay? Now by the FFI distribution, I mean the following. You sample small linear combinations of powers of x and you give the image of the thing. And that's your representation, that's your FFI distribution. Okay? So in some sense, what it is saying is, it is saying that, like, okay, like in the talk you can consider that that beta is 1 for simplicity. So what it is saying is, it's saying that, okay, in the private you have a good representation, but in the public it's kind of a bad representation. I will come with some example later, but this is like the whole idea. Like it's taking some good representation and it's returning some bad representation. Okay. So what is the problem? The problem is very simple. I give you the public representation of the finite field and arbitrary many FFI samples. You have to decide if there is unusually short representation of these samples or they are just picked at random. Okay. So this problem was initially introduced at PKC 18 to do some kind of FHE scheme, and then also some signature scheme was proposed using a similar kind of assumption. Okay, let's see some toy example. Like for simplicity, n is 16 here, and your q is 32771. First is this little f, which is kind of a hidden, which is sparse and ternary. Okay, and then you have this capital F, which is the public representation of the finite field, which is just picked at random, which is irreducible. Phi be the isomorphism from the first to the second representation, and this is what my phi is. Like if you do the minimal polynomial of this phi, it's this little f. So basically this phi is one of the root in the different representation. Now let's look on the representation in the both bases. So for the first, you have this very small linear combinations of powers of x, and this is the image, which kind of taking small representation and just returning some weird, thing. You can see like all these things are very small, but the image is kind of very weird. And the problem is the following. I give you these things, these representations along with this capital F. You have to tell whether there is some kind of a weird, if there is very small representation in some hidden finite field representation. That's a problem. Okay, why do I, yes.
By small, do you mean small coefficients?
Yes. Like here, like by small, I mean just say ternary, like 0, 1, and -1. Okay. Okay, uh, during this paper, like the way the author's approach to solve it is by lattice methods. So how? So you can consider the lattice generated by the columns of the matrix whose rows are the samples that you have got, and then it's easy to see that this kind of constitute a lattice, and uh, if the samples are indeed FFI, there are very unusually short vectors inside it, because there is kind of isomorphism that will take you to this good representation. So by definition, there exists some unusually short vectors inside this lattice. But if they are just picked at random, like if the AIs are like just picked at random, it's highly unlikely to have such small vectors inside the lattice. And if you can distinguish the two cases, then you have a distinguisher. But as I said, this is already known to be a very hard problem, and we don't know how to kind of have a solution to it efficiently when this n is sufficiently large. Okay. Yes. Yes. Sorry. So they are just picked at random. Like you can take any distribution which kind of gives small elements, like small coefficients. Like you can take it as a uniform between 0, 1, -1, or maybe a discrete Gaussian, which has a small things. Okay. Okay. So yeah. So here I have taken like a ternary 0, 1, -1 uniform at random, but it really does not matter. If it's small, it's okay. Okay, that's good. Okay, so this problem was also used to do some fully homomorphic encryption scheme, and the idea is to use these encryptions of 0 to encrypt bits. So I'm not going in a very thorough way how this was done. I'm giving a very oversimplified version of the construction that they had. So how this encryption, this fully homomorphic encryption works? Well, it works in the following way. To encrypt a bit, what you do, you take some FFI sample and you multiply with p, which is 2 in rest of the top, and you encrypt the bit. Okay. Now to decrypt it, you use your secret isomorphism to go back to your good representation, and you take this mod p operation. And since this part is very small, so if you take this mod p operation, everything cancels out, and you get the bit that was encrypted. It's very simple, right? What you can also do is you can add to ciphertext and you can decrypt it, and the thing that you will get is basically the addition of bits. The most important part here is even if you do the product of the ciphertext and you do the decryption, since your minimal polynomial here, like since this little f is sparse and ternary, when you do the product, your norm is still going to be small. I'll show you some example here, but believe me, since this choice of little f was sparse and ternary, if you do this product of the small representation, it's going to be small. And then if you do the mod p operation like before, and everything cancels out, and you get the product of the bits. So in the paper, they have shown like if you take your modulus sufficiently large, which is sub-exponential here, the construction that I have is kind of a fully homomorphic encryption, and it's nice. Like it's a new way of doing a fully homomorphic encryption using this new assumption. Okay, this is the thing. And okay, like let's see some example, like some concrete example. So when you do the operation over fq, you first consider this operation over z, means over integer, and then do this mod q operation, right? Like let's see the what thing happens when you do over z. I mean from z to fq, I mean it does not really matter, but just consider now instead of taking this base thing fq, let's consider it z, like over integer. and you take this minimal polynomial which is like non-sparse. Okay. Now first I sample some small vector on this ring, and I see what the product looks like of this thing. This is your multiplication, right? You see, like in the first, the coefficients have grown to some extent, and if you go the cube, I mean, it has gone like crazy. Like now, I think it's very hard to even say it. And like if you do 4, I mean, I can't even write it in my slide. Like it goes like huge. So what I really mean is, if you choose your minimal polynomial non-sparse, there is no way you can control the noise growth. Okay, and because at the end you need to do this mod f operation, and everything kind of gets crazy. But if you take this minimal polynomial to be sparse and ternary, you see, like in the first, I take like before some small e, which has just ternary coefficient, and you see the square. And now you see that noise growth. I mean, it's not bad. I mean, you can store it, right? Now I did the cube. I mean, it's okay, it's growing, but not as crazy as in the last slide, right? You can actually have it. Like you do 4, 5, I mean, you can do it. And that's a point. Like you really need your this minimal polynomial to be sparse to control this noise growth. And this is very, very common in lattice literature. Like you need this kind of ring where the noise is kind of controllable. Like you need this smallness to be intact. You do multiplication, it should be small. Otherwise, there is no lattice-based construction. Like everywhere, you need this kind of operation. So, okay, this is just, I wanted to show like how the noise growth kind of acts for both the sparse and the non-sparse case. Okay, and okay, so just a second. So here, yeah, I mean, you really need this thing to happen. Like you need, when you do this small multiplication, you really need to be controllable. And then when you do this mod p, it cancels out. If it is beyond your q, I mean, the decryption does not work anymore. So you really need the sparsity to be there. Okay, that was what it was on the paper. Now let's see something very intrinsic on lattice theory, on finite field theory. So in finite field theory, like there is this thing called trace of a finite field element, which is basically the sum of all the conjugates. Okay, and we need three properties of the trace. The first, trace operation is linear. By linear, what I mean is if you compute the trace of alpha plus beta, this is actually equal to the trace of alpha plus trace of beta. Okay, this can be computed in a linear time. Like it's already very well known that okay, you can just compute it in polynomial time, no problem. The last thing, which is kind of intrinsic, is the trace is invariant under the basis transformation. It does not really matter what you are computing. What it really matters, you are computing the finite field element, not the representation of the finite field. And this is the consequence of the fact that the minimal polynomial is invariant. So trace is like the first coefficient, and everything follows, like trace, norm, and everything remains intact when you do this minimal polynomial on the finite field element. Okay. Okay. Now, since x is one of the roots of little f, the other roots are given by the Frobenius. Like this is like very basic finite field theory, and we define the elementary symmetric polynomial by the sum and the product of the roots. And let's define it using this sigma i's. They are the uh, elementary symmetric polynomials. Okay. Now, if I represent this little f by this symmetric polynomials sigma I, then by definition, since it's sparse and ternary, the first half of the symmetric polynomials are 0, and it's ternary in the second half. This is the by definition. I'm not doing anything. If this is the case, then we can explicitly find the trace of the powers of x in absolute value. And this is n when this power is 0, like this is just a, I come in a bit, uh, 0 in the first half of your powers of x, like between the interval 1 to n by 2 minus 1, and it's d in the second half if the corresponding symmetric polynomial is non-zero, and 0 if the corresponding symmetric polynomial is 0. Okay, this is like I show you how this is done, but this is what we will show in the next slides. Okay, before going to the proof, how do you define the trace of these powers of x? It's just the power sum of the roots, right? Like this is very basic. So what you get in the trace of 1, so it's basically 1 added n times, so it's n. Okay, there's no problem. What is trace of x? It's a sum of all the roots. So by definition, this is a sigma 1. And if you see the trace of x square, it's the power sum of these roots in quadrant in square. So you can represent it like using this simple algebra, and you can write it in terms of sigma 1 and sigma 2. Like similarly, you can do it for cube. You can represent the trace of x cube in the symmetric polynomial, like this. Same way you go for 4, and you can just generalize this thing using this Newton-Girard formula to have something bit fancy. But just trust me, this is just this adaptation of this formula in higher dimension. And though this term is written in the numerator and denominator form, they are in fact all integers. So there is no problem on defining over fq. So you just consider it as an integer. Just it's written in a way so that you have this magic formula to define the trace of the powers of x. Okay. So you can define the trace of powers of x in terms of the symmetric polynomials sigma i's. Okay, that's fun. Now, since the first half of the symmetric polynomials are all 0, this is by definition, there is no contribution of sigma j's in the summation, right? So there is no contribution in any way. So the trace of powers of x in this interval is going to be 0 or 0 mod q, whatever. I mean, does not matter. But it's going. There is no contribution on the trace part, just because your first half of the sigma j's are all 0. So it works perfectly. Okay. Now the interesting part is in the second half. Now, since the first half of the sigma j's are already 0, the only way that this sum can have a contribution is for this value rd1 and 0 elsewhere. Because if you take any two values over n by 2 and try to have some kind of solution on this part, it's going to go above d, so this is not going to be on the summation. So the only way you can have a solution on this thing is when this value is 1 and 0 elsewhere. So the only way you can have the trace of powers of x is something like it's a plus or minus and this part d. So you know the trace of that in absolute value. It's going to be d when the corresponding symmetric polynomial is non-zero. But if it's 0, it's not going to contribute again, so it's going to be 0. Okay. So why is it useful? So basically, just wanted to show. So basically, we have shown that okay, this absolute value of the trace in powers of x is n when this d is 0. It's 0 in the first half of d, like between 1 to n by 2 minus 1. D when the corresponding symmetric polynomial in the second half is non-zero, and 0 if the symmetric polynomial is 0. And these are all smaller than n. Like it's this d is always less than n. So all these values are all less than n. Okay. So now if you take the small linear combinations of powers of x and you compute the trace, well, by linearity of trace, we know this value is going to be upper bounded by some factor of n square, because I just did this worst case bound, and now we know like the first half is all zero, but okay, we can have some factor above, but does not really matter. But it matters that some kind of upper bound of the trace of powers of x. And because the trace is invariant under basis transformation, the trace of the FFI samples are also bounded in absolute value of this factor of n square. This is just the intrinsic property of the trace. So just keeping in mind, we have a polynomial time algorithm to solve the decisional finite field isomorphism problem. How it works? Okay, let's consider this Q to be 4 times beta times n square, and then given k many samples, you just compute the trace in absolute value. If they are all upper bounded by this factor of n square, okay, these are going to be FFI samples. But if not, they are just uniform samples. And because the trace is uniformly distributed over FQ, we have an algorithm to solve this problem with advantage 1 minus 1 by 2 to the power k. So, okay, it can happen that even if you take all the FFI samples, they all lie in the small thing of trace, but it happens with very small probability, so we can just kind of avoid this thing. So we have an polynomial time algorithm which solves this decisional finite field isomorphism problem. Now, in some cases, when we construct cryptography, it happens that even the underlying problem remains easy, the cryptographic construction remains hard. So, so the first thing was like, okay, can we solve, can we get a semantic attack on the FHE scheme? So it turned out that yes, we can also use this attack to get a semantic attack on the fully homomorphic encryption scheme. So in the semantic attack, it works in the following way. So it's a game between a challenger and an adversary. So since the bit was like 0 and 1, so it does not really matter who chooses the message. So what the challenger does is he gives some encryption of either 0 and 1, and the adversary has to tell whether it was 0 and 1. If he can solve it, he solves this semantic thing of the encryption scheme. So let's try to do it. Like the attacker gets the cipher text. Can he tell it was 0 or 1? Okay. Now, given the cipher text, what he does the trace computation like before. And for the first case, like let's consider P, which is 2, is not a divisor of n. That means like n is odd. Okay. Now, like trace is linear and so on. Any question? Okay. So you know that this trace is going to be this, and by definition, this trace is also small. Now, if you do the mod P operation, the first part cancels out, and what you get is trace of 1 or trace of 0. And if you do this thing, like the trace of 1 is n and trace of 0 is 0. So if you do this mod P, and since P is not a divisor of n, you get 0 and 1 that was encrypted. So an attacker who does not know the secret key at all, just getting the cipher text, he can just find whether it was the message or whether the message was 0 or 1, and that kind of solves the semantic security of the cryptography of the FHE scheme. Okay. Okay. Now, okay, like now if P is a divisor of n, suppose n is even. Now, if you do mod P, like it's 0 both the time, right? Like 8 mod 2 is 0. So you get 0 in both the cases when P is a divisor of n, and the semantic thing does not really work out here. So, but what we can really do is the following. We can pick some FFI sample which has the trace such that P is not a divisor of that of the trace of that thing. Yes.
Would you mind going back a slide?
Yeah. Sure. Yes.
Okay, so you're saying that
Mm.
you take the trace of CA and then you take mod P.
Yes.
What's stopping us from just taking CA and mod P?
No, no, no. Because okay. This is unless you have this small thing into account, like when you compute mod P and mod Q, this is not equal to mod Q and mod P. Unless this is small, you really need the trace thing to happen here. You need this to be okay. Like by small, I mean if you do the computation over Z and you do the computation of FQ, that remains same. So if you okay, like you take Q7, okay, and then you take something like 5, and if you do this mod P, it's okay. But now if your thing is over Q, then there's a wrap up, and if you do this mod P, this is not going to be same. You need this smallness to appear. Like this trace makes things smaller. Like it was initially mod Q. By trace, you're taking everything over Z in some sense. Then you are doing this mod P, then this part cancels out. Without doing this thing, I mean, you don't get this thing. Like it's all uniform thing.
When you say mod Q,
Yes.
Q is a. I thought Q was the fine.
Yeah, so Q is something prime.
Okay.
Okay. So, but you really need this trace. Like you cannot just, okay, given this, if you take mod P, it's not going to give you, like it does not cancels out. That's why you everywhere you need, I told you like several times, like you need this smallness to be there. Like if it goes over Q, like if you need to do this mod Q operation, you can't do the decryption. Also, you cannot do this thing. You need everything to be small. Like it's an element of FQ, but if you see it over integer, it's like same. There is no change if you do operation over Z or over FQ, like it's going to be same. Okay, that's cool. Okay, now here, okay, here what you can do is, okay, you can pick some FFI sample such that P is not a divisor of this dummy thing that you are considering. Then you can actually multiply this dummy FFI sample that you have picked out of nowhere, and then you compute the product and take trace afterward. Why is it useful? It is useful because now you have P times trace of some product plus the message times the trace of this FFI thing that you picked. Now, since by the definition of little f, we already know this product is not going to give a lot of growth, noise growth, right? Like this is the main motivation of taking this little f in the FHE construction. So after the multiplication, this thing still remains small, and if you take the mod p now, everything will cancel out, right? Now if you do this, so what you have is this message time this trace, and now I know that this thing is such that p is not a divisor of this thing. So then if you do this mod p like before, you get 0 if the message was 0 or 1 if the message was 1. And it really works because the queue is quite large, and you have this little f which is sparse and ternary, and you really can control the noise growth. And so we have a polynomial time attack of the semantic security of the FHE scheme that was really proposed based on this FFI problem. Okay. Okay, so just to give a last thought, even the decision problem is a polynomial time, but we don't know a easy way to solve the search problem. Like the search problem was to recover this phi, like the hidden isomorphism. It appeared that like the best way still we can solve this phi is by lattice methods. Like I really need lattice algorithms to solve the hidden isomorphism, but it still looks quite interesting. Like okay, like the decision is kind of easy, but the search kind of still kind of looks hard. So if you really want to have a look on it, this is the e-print version of the paper. Go to it, and like if you are interested, we can have a talk during the workshop. So if you have any questions, feel free to ask.